Now what I'm going to do is cover lecture 2. First off, your assignment, we're going to walk through this thing called My First MNIST. It's a Jupyter notebook, and I'm going to show you how to do that inside your Windsurf. Okay, but this is actually a very famous data set that we'll review that you should have watched a video for your last assignment, and it's called MNIST, and it basically is handwritten digits. And what we're going to do is try to identify what those handwritten digits are. They're 28 by 28 pixels long. So if you stretch out all those pixels to 784 is the dimensions, that is the input, and we'll find out that actually this problem is very easy for neural networks to do. For your assignment number 2, you're going to actually do this analysis for Fashion-MNIST and try to generate a low loss. You're going to try to reduce the loss and increase the accuracy of your neural network model. Also, you're going to read a Imperial College Machine Learning Neural Network blog. This summarizes quite a bit of what topics we covered so far. It can get a little bit technical, but it gives you a really nice sort of overview of everything that we should cover from the first lecture to the second lecture. So the Imperial College Machine Learning Neural Network blog is excellent. And then you're going to watch and summarize. This is the MIT introductory video. I think it really plugs in any holes in your knowledge about neural networks, and they do a really great job, and I encourage you to watch other resources. Finally, your vibe coding assignment is Elon, you're fired. So you'll take a look at that and read that. That will be posted up in assignment number 2. I think it'll be a fun assignment. Basically, you're trying to create a prediction model to understand if someone can make more than $50,000, and you're given a bunch of features. And the data is more like a real-world data set, meaning that there's missing observations, and so you're going to have to sort of use that. Use Windsurf, use all the tools that we mentioned before, and give it a shot. Okay, so today what we're going to do is take it from the Perceptron to the basic neural network. And after that, we're going to look deeper inside what the neural network is doing. And then we'll do the exercise. And I think the exercise will give you a really nice framework of, so how is this done in terms of gathering the data and, setting up the model, estimating the parameters in the models, which we'll learn from the errors that are made. And it's learning through this technique called backpropagation. So you get the data, remember the data doesn't change, it goes through the neural networks and through the different layers, it makes a prediction. Usually there's some kind of error. Now you take that error and you backward propagate it, okay? And when you backward propagate, what you're trying to do is you find the gradients for each one of the parameters. So that includes the weights and the biases. And because of the chain rule and the way it's set up, you have to work backwards, one layer at a time, okay? And then we'll talk a little bit about inference and how to deploy these neural networks, and then you'll have your assignment number 2, which is due before next class. So perceptrons to the basic neural networks. Here's actually a picture of your neurons in your brain, how they're all connected. So our sort of framework here is the cell nucleus. This is a neuron. This is a very simplification, let's say. And so we see that the input signals, so that's the data coming in to the dendrites. The dendrites could capture that information, aggregate that information, and it goes into the cell nucleus. Now, if it reaches a particular threshold, it will activate and send the signal through this axon into the end. And so when you think about the perceptron, this is basically what I'm going to overlay it here. X1, recall, are the data. W1 is the parameters that are multiplied by the data. And then you aggregate that up. With a summation, you add the bias. Now remember that the data doesn't change. What's going to learn is the weights and the bias. Those are the parameters. We're using the summation operator here. Now you get a scalar value, which is just a number, and you will take that one particular number and put put it through an activation. Here is a very simple stepwise activation. If this value is greater than 0, then it activates, you get a 1. If it's less than 0, if it's greater than or equal to 0, you get a 1. If it's less than 0, you get nothing. And so this is basically the signal that is transmitted through the axon when it hits a particular threshold. Now, we know that there's many different activation functions. We'll talk a little bit about those. And then this gives you the signal, and that output signal is put into the next sort of layer, okay? Now, I want you to really sort of think about how this perceptron is the building blocks to the neural network. And this visualization is supposed to help you. So here again is a very simple neural network: input layer, the hidden layer, the output layer. What I'm showing you here is actually here's one perceptron, which has 3 input nodes, and it's going up to the first hidden node. Here's the second perceptron, and here's in the hidden node, here's the third one, and then there's actually a fourth one. So that first layer, from the input layer to that hidden layer, you can see those are stacked perceptrons, and that's very important. So in order to understand neural networks and how they work, you have to really understand how a perceptron works. Now, in the next layer, you'll actually see now you have 4. Those signals become the input, and the output will be the first node in the output layer. In that situation, you have 4 now inputs into the final output node, which is the top node, and then there's also a secondary node in the output layer. And so those 4 inputs in the hidden layer now become, aggregated up, and then it becomes the output to the final layer. So that's the map between perceptrons and neural networks. So you can think of a neural network as a multi-layer perceptron with many different layers. What is a deep neural network? A deep neural network is actually very simple. We just talked about one hidden layer in this neural network. If you have 2 or more hidden layers in your neural network, that is considered a deep neural network. So anything that has deep learning or anything that has the word deep, it just means that it's a neural network, but you have 2 or more hidden layers. Okay, so now let's look inside these neural networks. What's inside? It's kind of funny. Let's just say I know a guy who knows a guy. And so this is Saul. And the reason why this is kind of funny is because, it's a bunch of perceptrons and they're stacked up on top of each other. And then you can sort of visualize a neural network as the next layer as another perceptron that's generating the signal to the next layer. So knows a guy who knows a guy, which is the perceptron, which is the building block. Okay, so it's called feed forward because the way it works is the data, x0, x1, x2, goes from left, and it goes to right across the weights, which is the yellow arrows here. It goes into the nodes, and usually there's an activation function. This could be a sigmoid activation or a hyperbolic tangent activation function. This will make predictions, and that information is fed forward through the network into the next layer. So now that first hidden layer becomes the output now to the second hidden layer. And again, you can see how the data is moving, how the information is moving from left to right. Initially the data and then the signal. Remember these now, at that point, you have parameters from the first layer, which is between the data and the first hidden layer. Now you have parameters that are multiplying. Every one of those arrows, you can think of it as a parameter, and then you have to add the bias to each one of the nodes. And notice how everything is flowing from left to right. And so that's known as a feed-forward neural network. Now, if you wanted the information to flow back into a node, it's possible, and that's called a recurrent neural network. But for the purposes of what we're doing for this lecture and this week, we talk about a neural network that is just pushing the information forward until the very end. It's probably a probability. It's a one node, so it's probably a binary classification. And so, or it could be, actually predicting the price of a stock. Either way, that's the end, right? Recall that in each in between, you have weights or parameters. Now these weights are the ones that are going to capture the learning. It's not the data, remember, it's actually the weights that will learn. And we'll go through and explain how those weights will learn. And just to give it away, it's basically the weights are going to be updated by their gradients. So the gradient is going to help determine which way, think of the weights as dials, which way is to turn the dial. Okay, so we'll continue our deep dive into neural networks. We'll talk a little bit more into the activation functions. The loss functions are very important. And basically, you'll see about 2 or 3 different loss functions. We'll try to dig a little bit deeper into backpropagation, but more so, I just want to give you the intuition and talk a little bit about gradient descent, which is just a derivative. But what complicates this is you have to use the chain rule because it's a function of a function of a function and so forth, depending on how many layers you have in there. So I'm just trying to give you the intuition. The math is not necessary. This is a master's level class, so we're just going to try to give you guys intuitively what is going on here. Here is a great website, and I encourage in class, if we're in class, we would stop here and we would work through some of these examples. This is the playground. I encourage you to go there. There are different data sets that you can use, and it's very easy to add more neurons to a particular layer of the neural network, and it's also easy to add more layers. And the task at hand is separating the blue dots from the orange dots. And under data, there's 4 different data sets, and one of them is very complicated because you have this one right here is the concentric circles, or basically you want to separate the orange from the blue. If you just try to use some kind of linear activation function, you'll see that you can't do that. You need a nonlinear activation function. And when you hit that play button, it actually generates, and you can see it sort of trying to update the weights, and you can monitor the loss function. So this is a really good website to build your intuition. I would try, if I were you, to use this and try to separate the blue dots from the orange dots and use the different data sets. So there's 4 data sets here. One is pretty complicated. You'll see it's basically spiraling blue versus spiraling orange. And so I think that this is a great place to build lots of intuition on this. You can play around with different activation functions. There's other parameters here that you can also sort of use, and you can't break anything. So it's a very robust, and it's publicly available, and also I think it's free. It is free. Okay. Now, let's talk a little bit about the sigmoid function. Let's really sort of dig in here. So this sigmoid function is 1 over 1 plus e to the power of minus x. So if we think about that and we put 0 in, if we put 0 in for x, then it's 1 over 1 plus e to the 0 power. We know e to the 0 power is 1, so it's 1 over 1 plus 1, so it's 1/2. So when x is 0, the f of x, or the sigmoid function, takes the value of 1/2. Now let's make x, very, very big. So imagine x is like, 100,000, right? So now you have 1 over 1 plus e to the minus 100,000. So e to the minus 100,000 is 1 over e to the 100,000. So that's 1 over really large numbers. So if you have 1 over a very large number, that's pretty much 0. So you have 1 divided by 1 plus 0. So 1 over 1 plus something close to 0 is 1. So is x, if you go on the right-hand side of the sigmoid all the way far out, you'll notice that when x is very large, then this sigmoid function will take the value of 1. And indeed, you can see it sort of, approaching 1 asymptotically. It never really quite reaches 1, but it gets very close. Now, if you have negative number, so now what you do is you put 1 over 1 plus e to a very big negative number, and the minus will become positive. So it's 1 over 1 plus e to a really large number in the exponential of the e. Well, we know e to the really large number is a really, really large number. So now you have 1 over 1 plus a very, very large number. So 1 over 1 plus a very large number is 1 over a very large number. So 1 over, you can think of it as millions, right? 1 over millions is getting closer and closer to 0. So you can see on the left-hand side of the x, when it's negative and it's very large, it starts to approach 0. Now, that kind of intuition, I think, is important to sort of have of these activation functions, specifically for the sigmoid. The other thing is, notice that the range, which is the values that the sigmoid can take, is between 0 and 1. So it's all positive numbers. Now you may say, well, what if we want to have negative activations? So somebody thought that up, and so they introduced the activation functions with the hyperbolic tangent, which allows the range to be from -1 to 1. Okay, and some of the advantages here for this activation function, notice that everywhere it's differentiable. What does that mean? Well, you can take the derivative, no matter what the x value, it's a very smooth function, it's differentiable, it's monotonically increasing, and so forth, right? Some of the disadvantages, and this is sort of subtle, is the vanishing gradient problem, because basically what happens here, and we'll cover this a little bit later, when you start multiplying these gradients together from layers to layers to layers, once you hit 0, then it tends to get, it's hard to get out of that 0 spot. That's known as vanishing gradients, and that provides some, issues with training a very deep neural network with many, many layers. Okay. Now, the next one, as we mentioned, is hyperbolic tangent. And the takeaway here is, as x is very large, it goes to 1, but now as x gets very, very small, it goes to -1. So now the activation function is bounded between -1 and 1, so it allows for positive activations and also negative activations. And in certain situations, you may want it to go negative, and I won't go through the intuition here, but you can see it's also e to the power of something, okay? The next activation function, you've seen this in the first lecture, is ReLU, which is a rectified linear unit. And you can think of this as the terminal value of a long call position with a strike of 0. So when x is negative, and whether it's a small negative number or a large negative number, it's pretty much 0. It's 0. It's flatlining. The slope there is 0. If x is greater than 0, it starts to become a positive number in a linear fashion, so a 1 for 1. Now notice that this activation function is differentiable everywhere except for when x equals 0. When x equals 0, you can't take the derivative there because it's the kink position, right? So this activation function has that sort of property here. People try to fix this kink, and you'll see a little bit later. And then notice that the derivative on the left-hand side is 0, so you also have the vanishing gradient problem, or the problem with dying, the ReLU, they call it. So people have tried to fix that, and so instead of having it flatlining there on the left-hand side of 0, they make it sort of a small positive number. So you can think of that as like 0.1. So it's a positive slope. It's not 1 for 1 as when x is positive, but it's sort of a positive. It's not 0, but it's a small positive of 0.1. Okay, and so this leaky ReLU is pretty popular. And how do they find these activation functions, or how do they know if it's useful? Well, they empirically test it with the data, and they look at the loss. Does the loss go down further? Does the model do better in terms of making predictions? Is the accuracy going up, and so forth? So a lot of these activation functions, and there's a whole slew of them. You can actually check on Wikipedia. In the early days of neural networks, they tried as many, that worked, and these seem to be the ones that work pretty well. Okay, now let's move from the activation functions, which are inside the nodes. What I didn't mention here is you can put whatever activation function you want in each of those hidden nodes, or you can use the same activation function. Most people will use the same activation function, let's call a leaky ReLU, or they may use a sigmoid. And it is a hyperparameter which activation functions you want to use, meaning that you choose that before you even set up the learning process, right? And you can actually compare them against each other. So now the next thing I want to sort of discuss here is a loss function. And this is basically at the very end of your neural network, you're trying to do something. You're trying to make a prediction. Usually you're trying to predict y hat. You generate y hat, and you're trying to predict the truth. And most people call the truth y or t. So basically you make an estimate, a y hat or a prediction, and you compare that to the truth. And usually there's errors, and this error is taken, which is a good thing. And you take that error and you bring it back through the network, and you try to get closer to the true value. And this is where the learning occurs, and the weights are adjusted so that the error starts getting closer and closer to 0. There's different ways to measure this error, and these are the loss functions. And the loss functions depend on what you're trying to do. So if you're trying to predict stock prices, which is generally thought of as a continuous variable between 0 and some large value, then you have mean squared error. And you should be familiar with mean squared error because that's what they use in regressions, the ordinary least squares. The other one is if you're trying to predict a classification, like is there cancer or no cancer, is it spam or not spam? That's a binary decision. It's either 0 or 1. So that's a different type of loss function that you want to compute. We'll see that here in a second. Or it could be a multiple decision. So it could be is the prize behind door number A or door number B or door number C? So now instead of binary, you have 3. So we can have more than 2 sort of choices, categorical choices. In the MNIST problem, for the digits, you have to choose between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So is the digit one of those categories? And there's 10 categories. Okay, so loss functions are important because this is the objective of the optimization. It provides a single value, so you can actually see if the loss is going down, and that's what you want to do. It's also problem specific. I was mentioned whether you're trying to predict stock prices with a continuous variable, or you're trying to predict some kind of discrete sort of value, such as binary or categorical. But both of them are generally solved the same way with gradients and backprop. We'll cover that in a little bit. But let's look at some of these loss functions. So here's an example of the mean squared error. You can see that y is the truth minus y hat, which is the predicted. That's typically how people write it in econometrics or regressions. Sometimes in machine learning, they'll use t for the truth, but basically you'll make a prediction and you subtract off whatever the true value is. And notice whether you do y hat minus y or y minus y hat, it really doesn't matter because you're taking that to the second power. So if it's negative, then squaring it will yield a positive value. So this is mean squared error. And basically you're summing this over each of the observations. You can see on the left-hand side I have an arrow pointing to the minimum value here. And there is basically a Python implementation. You can see the function, what it looks like, using NumPy, mean, y is true minus y predicted, raised to the second power. Okay, so this functional form is actually very, interesting. It's y to the second power. You could have done it to the fourth power, the third power, the fifth power, and it's like an averaging 1 over n. And so, some people say this is the first moment is the mean. This is the second central, sort of measure of the second moment. You can think of it as kind of like minimizing this differential error. And so that gives you a sense of mean squared error. The other one is binary cross-entropy, and this one is a little bit more complex because basically what happens here is if you say the y value, the true y value is 0, you'll be optimizing the left-hand one, which is basically, notice that 0, this binary cross-entropy function is getting very small, right? However, if you're saying, hey, this is actually 1, the true value is 1, notice that it kind of flops. So basically, the minimum value of this binary cross-entropy is now at 1, right? Not at 0. So binary cross-entropy is a little bit confusing initially for students who don't have their intuition because it's one function one way and another function the other way, and it sort of depends on what is the true value of y, right? you can look inside this summation, and you can actually see that when y equals 1, the second term, 1 minus 1, is 0. So you get basically the first term, right? And now when y equals 0, when the true value of y equals 0, that y minus, I'm sorry, y times the log of y hat, that term drops. And then 1 minus 0 is 1. So then you have log of 1 minus y predicted. So you have to be a little bit careful here. But this is the a binary cross-entropy function, loss function that is used. We're going to use something similar here. And in your, okay. Categorical cross-entropy is basically this function, and this is used for more than two categories, and this is the one that will be used in your MNIST. Actually, the loss function there, we'll talk about when we get there, but as this community continues to develop, they made it much easier for people to use neural networks. We'll discuss it a little bit there, but it has to do with taking the y value, which is 1 to 9, and then converting that into a one-hot encoding, which means that you have a vector of 10 numerical elements, but in one of the elements it's 1 and everywhere else is 0. And you do that sort of 10 times, so those are one-hot encoding. That is sort of incorporated, you'll see a little bit later when we go through the Jupyter Notebook, directly into the calibration of the problem, you'll see. So that they've made it much easier now than before. Okay, so the problem that we're going to try to solve is something that was solved by this professor, Jan LeCun, who's super famous. He's the chief AI scientist at Facebook. He also is a professor at NYU, I think, Courant. And this is what he did. He had a bunch of these handwritten digits, right, from 0 to 9. And the task was, can you use a neural network and predict what value it's seeing, right? Seeing in terms of the pixels, right? So this bank check recognition system, by and large, and this whole sort of industry, Jan LeCun was the one that actually got this to work. At that time, people didn't know if this was going to work or not. And now it's become a very easy problem to solve. And there's a lot of educational aspects. So, we covered a little bit of the iris, your first homework assignment, your first lecture. This one is, you'll see, is a nice data set to introduce the neural networks for students so that they can really examine it. In the data set, you have 60,000 examples for the training and then 10,000 for the test. So in order to create a model, you want it to make robust predictions out of sample. So usually the way they set it up is there's a training data set they use to create the model, and then they see how well it performs out of sample by reserving some portion of the data that's not used in building the model in order to test it. You're supposed to only test it once. The test set, or some people call it the validation set, is used. You're supposed to use it only once, and then you'll get a biased prediction of how well it worked. So MNIST is, the data set is very popular, and you can see a lot of blogs and different ways that people sort of use this to teach students about neural networks. Okay, so here's an example. It's the number 2. Each one of these, it's 28 by 28. You can think of this as boxes, 28 by 28 boxes. And the X1 is the first box, next to it X2. Now, if you get a 28 by 28, each of the boxes has a value. And you can see that when there's nothing in there, it's usually 0. And then when it's some kind of value, it could be kind of a, gray or black. And it goes up to, each value goes from 0 to 255. There's 28 boxes and rows and 28 columns, so the 28 by 28 is 784. So this basically becomes a 784 dimensional vector of numerical values. A lot of it is 0, and there's numbers in there. So that is your input layer. Compare that to some of the things that we've already seen. For iris, there was only 4 sort of features for each one of the irises. But here we have 784 features, right? And we take that data, we put it through the hidden layers, right? Here we have 2 hidden layers. And now the number of hidden layers and the number of nodes in each of the layers is a hyperparameter. So you get to choose that, right? And now the output has to sort of map into, one of 10 categories, right? What digit is it, right? The blue is basically a softmax, so you get whatever value is in softmax is a way to normalize the output so that it looks like probabilities, so they sum to 1. And you basically choose what is the highest probability value here, for example, is 0.7. And 0.7 is associated with the 2. So it makes the prediction correctly that this is what it's looking at is a 2. Now, we're going to talk about this, about epochs, but how do you send data through this neural network, and how often do you update the weights? Now, you can send one observation at a time. So remember the 60,000 images. You could send one image at a time and then update the weights. That's called stochastic, there's mini batch, there's stochastic, and there's batch. Batch is you put all the data in at once. Imagine you put 60,000 data points, what is it called? Pictures in at once, and then you generate the error, and you also take that error and update the weights. Or you can do it one at a time, which you take one observation, one of those pictures, and you put it in, and you update the weights, and you put the next one in, and you update the weights. That's stochastic gradient descent. Then you could do mini batch. Mini batch is basically you grab like 32 at a time or 64 at a time before you update the weights. And we'll talk a little bit more about that. But basically, how do you feed data through this neural network? And how do you update the weights? What's the frequency of updating the weights? And there may be some reasons, if your data set is not very big, that you can do batch, and there may be other reasons why you get so much data within a day that you may want to do mini batch, where you're chopping your data up and just sending thousands in at a time. Maybe you got 100,000 data points in a day, right? Or there may be reasons why you want to update this every single observation. Okay, so the data goes through, we forward propagate this data, and then we come up with some kind of prediction. We compare that with the truth, right? Because we know the actual labels for these these digits, these pictures, and we can actually calculate a loss. We're going to use a particular loss measure, right? Then the other thing is, after you calculate the loss, you have to push that error back through, and this is called backpropagation. Backpropagation, in particular, we're not changing the data. What we're trying to do is capture the gradients. So the gradients are going to be the things that update the weight. So every weight here between the output layer and the layer 2, and between layer 1 and layer 2, and between input and layer 2, there's a lot of weights there and biases. We need to adjust those weights. And the way that we adjust those weights is by using each weight is associated its own gradient. So we're going to use the gradient in order to adjust all those weights. So you can think of it as dials. We're turning these dials for each of these weights to make it closer to the prediction, closer to the truth. Okay, so what's the intuition and backprop? It's an algorithm used to train the neural network. It calculates the gradient of the loss function, okay, with respect to the network's weights. So just imagine how many weights are in the network. And it allows us to update these weights in a direction that reduces the loss. So basically, the learning is occurring when you're updating these weights, and the weights are learning to capture whatever task at hand, which here we're trying to predict the actual labels for these handwritten digits, right? Okay, so you have to do the forward pass first. You get the error, and then you use that error in the backward pass. Now it gets a little bit complicated because in order to calculate the gradients, you have to use a thing called a chain rule. Because remember, this is a feed-forward network. So there's a function inside a function inside a function, depending on how sophisticated or how deep you want to make your neural networks. And in order to sort of update each of the weights and find the gradients, you have to start at the very end. And we'll show you a little bit of intuition on how that works. Updating the weights is very simple. Once you get the gradient, basically your new weight is equal to your old weight minus some kind of learning rate times your gradient associated with that weight. So here's a very simple example. It's here just to get you some intuition, build some intuition. There's one node, input node. The first weight is 0.5. Then there's a hidden node, but that it's gone through one activation function. Then once you get the output out of that activation function, you hit it with another weight, W2, and then you make your prediction Y. So in this example, let's just start out with some numbers. Let's say the first weight is 0.5 and the second weight is 0.5. And the first weight is between the input layer and the hidden layer. The second weight is between the hidden layer and the output layer. And you have an activation function. So first you take x, which is, let's just say 2. And then you multiply that by W1, which is a weight. So 2 times 1/2 is equal to 1. And then you put that through the activation function. And below you can see what the activation function is here. So when you put this value into your activation function, at 1, you get up here and you read it off, you get something like 6 point something or almost 7. So let's take a look here. First you do 2 times 1/2 equals 1. You put it through the activation function, so you get 0.73. So 0.73 is the blue line going off to from 1, x is 1. You put it in there, you get the blue line, and you go across, and that's going to be 0.73, okay? Now you take that 0.73, and now that becomes h. You multiply that by 0.5. So 0.73 times 0.5 is 0.36. Now that becomes your prediction. Now remember that the truth was y equals 1. So now you compare 0.36 with 1. And here, let's just assume that the loss function is some kind of mean squared. Let's just assume it's 1/2 y, which is the predicted, minus t. Y truth is t. Quantity squared, y the 1/2. It could be any sort of value there, because when you optimize this, you take the derivative, but that's a constant outside, and the other side is equal to 0. So you can basically multiply. It just makes the derivative easier, because when you take the derivative of mean squared error, which is raised to the second power, the 2 pops out, it hits the 1/2, it becomes 1, but it really doesn't matter because that's just a constant. But basically, now you can look at this loss value. Let's say the loss value is 0.20. So what we want to do here is to minimize the loss. We know that in this example, since y, the truth is actually 1, in the mean squared error loss function, we know it minimizes at the value when the y prediction is equal to 1. We're way over here. We're not close, right? So we need to move closer down towards 1. Okay. So here is the chain rule in action. So we start at the very end. What is the loss with respect to y? So how sensitive is the loss with respect to y? And then we move further down. How sensitive is y with respect to W2? W2 is the weights between the first hidden layer and the output layer. So we're going to calculate what is the derivative. How is the loss function affected by small movements in W2? And then we also have to find the gradient for W1. How much does the loss function move relative to W1? But we can't get to the gradient for W1. We have to do the gradient for W2 first. So we do the math here, and you can sort of, take a look. Remember, gradients, and these are all numbers because we have empirical numbers here. So the loss with respect to y is going to be basically minus 0.63. And then if you do the derivative of y with respect to W2, basically you can use this formula. We know that y is equal to h times W2. So when you take the derivative of that, you get h. We know h is 0.71. So now we multiply the gradient of the loss respect to W, and then the derivative of the derivative of the loss with respect to W, and then we take the derivative of Y with respect to W2. This is going to be basically multiplying minus 0.63 times 0.73, which is equal to minus 0.46. So we know the gradient associated to W2, the parameter. So small movements into W2, how does that affect the loss function? If you increase that weight, it will reduce the loss function by minus 0.46, okay? So that's very important because now we know how to adjust W2 in order to reduce the loss, okay? Now we also have to calculate the gradient, okay, of with respect to W1. And here's the formula. You can walk through the math. Basically, you can see here, you get another value. So now you have a gradient for W2, and now with that information, you can calculate the gradient for W1. And with that information, now you can update. So these are the gradients. So recall that the first one is the gradient of the loss with respect to W2 minus 0.46, and the other one is minus 0.12. And so when you put that, you're going to use this formula whereby the new weights, W1 and W2, is equal to the old weights, W1, minus the learning rate. Here we set the learning rate, so this is a hyperparameter where you set it at 0.1, and those learning rates are multiplying by the gradient. So we use, for updating W1, we use the gradient for W1. For updating W2, we use a gradient for W2, and these are the new weights. So instead of W1 being 0.5 and W2 being 0.5, now they're getting adjusted a little bit higher, okay? So this is the sort of the summary. Before the update, we had 0.5 and 0.5 of the weights, recall. And then after the update, you get 0.51, 0.54. So we've increased the weights on both of these. We kind of turned positively W1 and W2 a little bit more than W1. Here we have the hidden activation, and then we have the output. Notice the output is getting closer to 1, and the loss 0.2 is now getting smaller to 0.17. So this is sort of working as we expected. Okay, let's stop here. Now for the key takeaways here, backpropagation uses the chain rule from calculus and is efficiently calculates how each weight contributes to the overall loss. And remember, when you have a sigmoid function in there, you also need the derivative of some activation. The derivative of a sigmoid function is sigmoid times 1 minus sigmoid. You can sort of, prove it to yourself. But basically what happens there is that the chain rule becomes a little bit more sophisticated, and so you have to sort of work out those derivatives, right, for the activation functions whenever you're working backwards. Gradient descent is used to update the weights. Each weight has its own gradient, so it has its own sensitivity to the loss function. So W2 was different from W1. And imagine if you had a very large neural network. For every weight and the bias, which are the parameters, you will have associated a gradient. How does that changing of that parameter affect the overall loss? And that's very important to know, and that's how you're going to adjust the weights. The other thing to remember here is that you can only work from the farthest, the parameters closest to the loss function, and you have to work backwards because you can't calculate the next gradient in the next layer unless you calculated the previous layer, which is closer to the loss function. So that's why you have to work backwards. It's iterative. And the learning rate is a parameter that you choose. Now you have to be careful with the learning rate, because if you make the learning rate too small, like in our example is like 0.1, but if you make it 0.0001, it may learn too slowly and use a lot of computational power, and it'll take you a long time in order to get to the optimal solution. If your learning rate is too big, so say instead of 0.1 you use 1 or 10, you may diverge, or you may be bouncing back and forth, and you may never get to the optimal point. So the learning rate is something that you have to sort of, try different hyperparameters. Some people do 0.1, 0.01, 0.001, 0.001, And so depending on how you set this up, it's important to sort of understand, that the learning rate is a hyperparameter. Remember, you can evaluate that by just looking how the loss function is getting reduced over time. Okay. Here's an example of sort of gradient descent in action. So you can visually sort of see how this will work. On the left-hand side is some kind of optimization of, you can think of that as a loss function. On the right-hand side that you should be more familiar with is kind of fitting a line to the points, right? So that's like a regression. Now, there's a danger between underfitting and overfitting. So here's an example. Suppose that we calibrated our model and, first we underfit. So, maybe we're naive about using activation functions and we just use linear activation functions and we try to separate the orange guys from the blue guys. And unfortunately, we don't have enough complexity and sophistication in our model. And so it doesn't do a very good job. That's underfitting. Most of the times people don't underfit, they overfit, because it's very easy that you'll see a little bit later in order to add more layers to a neural network and add more nodes inside each layers. So most of the times people who are building these things, it's very easy to overfit and they over-parameterize the models, meaning they put too many parameters into that model. Here's an example of overfitting. Notice that the red line is just perfectly separating the blues from the oranges. However, ideally, it's probably sort of like in the middle, right? And this is more of an art, right? So you notice that the green line sort of separates it. There's two observations that are misclassified, but maybe that's just bad data or something like that. It seems to be the pattern is more of this sort of, circular thing versus the overfitting pattern. But this is done, and there's a lot of diagnostic tests in order to see if you're overfitting that we'll talk about a little bit later. Ideally, you want your loss of your training and sort of your task to go down at the same amount. Your training loss will continue to go down, but if your testing loss doesn't go down as much, then it's a sign that you're overfitting. You've overfit. So you may want to back up and try to use a particular model that doesn't do that, right? And this is basically this regularization technique. So there's different types of techniques in order to help you build a more robust model. This is one of many types of regularization. So regularization means that you're attempting to create a robust model. You have very powerful tools that will overfit very easily. So here on the y-axis is a loss, and on the x-axis is epoch, so how many times you run the data through the model. And the blue line first is the training, so the loss decreases as you train and you fit the data more and more. At some point, you've overfit, which is further down on the right-hand side. You can think of that as basically you're putting a boundary too close to the actual data. Now, notice that, how do I know that's overfitting? Because when you do the validation or test set, as you're running this over and over again, notice the validation is diverging from the training. The training continues to reduce the loss. However, the validation set, when you try to use that overfit model, it's generating more and more, it's increasing the loss, which means that it's making mistakes, right? So when the validation increases in terms of loss and the training decreases, that's a sign that you've overfit the data. So one technique is to just make sure and take that model where both of them are sort of decreasing. And this is called early stop. So you stop it right where the arrow is and use that particular model. Remember, as you add more, as you go through the data more, you run more epochs, the parameters are adjusting, right? So you have different models at each of the epochs. So you can use an earlier model. That's basically how it works. There are other types of regularization, but there's L1, there's L2, there's putting penalties on the weights. The intuition there is that you want to keep the weights closer to zero, and the more the weights diverge from zero, the higher the chance of overfitting. Here are some methods that you'll see that we'll use: .fit, .evaluate, later on. Okay, so what does it mean once you get this model and you're pretty comfortable? How do you deploy this model? Now, deploying a model, you can do it in the cloud. One thing is when you get new data and you want to make a prediction, that's typically called inference. So that's you have the model set, you're pretty happy with the model, now you want to put it in production, you want to deploy the model. Now you want to make inferences out of that. If you think about ChatGPT, whenever you guys are interacting with ChatGPT, it already has been pre-trained. So all the stuff has already been done for you. Now you're using it in order to make a prediction of the next word. So you're making inferences using a pre-trained model. So you'll hear about that. Here we'll also discuss a little bit about stochastic batch and mini batch. Just recall that batch is putting all the data in and estimating the parameters. When do you estimate the parameters? After you put all the data in? Do you estimate the parameters after each one observation the data goes through? That's stochastic. And then mini batch is you estimate the parameters after you put 100 observations in at a time. So that's kind of in between batch and stochastic, which is mini batch. So those are the different ways in order to update the model. But the point here is when you deploy, you're making inferences using that model, and that model has already been pre-trained or calibrated, right? The pre-training, the calibration side are the ones that cost, on the order of 30 million to hundreds of millions of dollars. Inference is not as expensive, remember, because all the parameters have been reasonably set in the pre-training process. Okay. So what we're going to do we're going to do this in Windsurf is these are the 8 steps. One is you're going to set up and import libraries. 2 is we're going to load the data, MNIST data. We're going to use TensorFlow Python 3.11 because that's the one that makes it very easy to get the data out. We're going to pre-process the data, basically normalize it, make it closer to 0. We will lay out the architectural structure of the neural network model. You'll see a little bit later, it's very easy to change that. Then we will train the neural network model, and we'll look at the loss. Hopefully the loss will go down and the accuracy will go up. We'll also visualize some of the training process. So it's basically we're going to watch the loss numbers go down. And then we'll evaluate that model once we find a reasonably good model. And remember, in the MNIST data set, it's very easy to find this model. We'll evaluate some test data to see some predictions, and we'll actually make some predictions, and that's called inference. So step 1 to all the way to step 6, that's pre-training. So this is where we're getting the data and doing all these things and getting the weights updating through their gradients. And then once we have a model that we feel comfortable with, now we use it. You can think of it as deploying it or putting it in production. Now we want to send it and make inferences, right? Because these models have to be useful.